What is nuclear magnetic resonance? How to trigger it? These are the topics we are going to talk about in the next few slides. Here the first segment is about resonance in general, which says that in physics, resonance is the increase in amplitude of oscillation of an object exposed to a periodic force whose frequency is equal or very close to the intrinsic frequency of the object. For example, if we have two cell phones that have the same intrinsic vibration frequency, then the vibration of fork 1 will be transported over the air to fork 2, making the same humming sound in the air. We can verify this by holding fork 1 to stop the vibration of it. Then you can still hear the humming because fork 2 is still vibrating. The important thing we have learned from this phenomenon is that an object that has a periodic vibration of circulation frequency can be resonated in similar way. Also included here is a link to a YouTube video that you can view at home. Unfortunately, we cannot embed even part of them into any lecture videos due to copyright. If we teach this in a classroom, we can play it on the screen. Now we can only rely on you to watch them at home. What is the definition of NMR, nuclear magnetic resonance? Here, it says that NMR is a phenomenon in which nuclei in a magnetic field absorb electromagnetic radiation whose frequency is equal or very close to the intrinsic magnetic resonance frequency of the nuclei. It is easy to understand that some nuclei being surrounded by orbital electrons must have magnetic moments, must somehow spin, and hence must have angular momenta. Knowing this is not enough. We've got to find a way to resonate the nuclei's periodic motion and convert it into some kinds of detectable signals. In 1938, Isidore Rabi managed to catch some NMR signal using continuous wave NMR. On the slide, it says that early discovery of NMR relied on detecting an absorption signal in a receiver coil optimized for a fixed frequency by changing the magnetic field strength, B0. Note that it was the current frequency of the receiver coil that was fixed, and the magnet was changed. With this technique, he could only collect one signal at a time. 4 scientists were rewarded for Nobel Prizes for the discovery. Otto Stern was rewarded a Nobel Prize in 1943 for his discovery of the magnetic moment of the proton and something else. Rabi, on the other hand, was rewarded a Nobel Prize 1 year later in 1944 for his resonance method for recording the magnetic properties of atomic nuclei. Felix Bloch and Edward Purcell also demonstrated the same thing in 1946, and they shared the Nobel Prize in 1952 for their discovery of new methods of nuclear magnetic precision measurement and the connection therewith. Soon people found that NMR signals can also be detected by tuning the frequency in the receiver coil to match the NMR frequency induced by an unchanged magnetic field. Just like how we receive radio broadcast by tuning a radio to the carrier frequency transmitted by a radio station using a radio. Note that with this method, the magnetic field strength B0 is fixed, whereas previously it was changed. In 1966, with modern computers being more accessible publicly, Fourier transform NMR spectroscopy was invented. The technique resonates M0 that contains the resonant frequency of all spins by applying a pulse of an oscillating electromagnet called the RF pulse, i.e., the radio frequency pulse, for a short duration, for example, 10 microseconds, and then collected time domain relaxation signals of all resonated nuclei simultaneously, followed by a Fourier transformation to transform the oscillating time domain data into frequency domain spectra. Remember we said that M0 is a summation of all mu j's. And for a molecule, the precession frequency of mu j's for different nuclei are different. Therefore, M0 is not simply a mathematic vector that contains only direction and magnitude. It also contains different angular frequencies in one entity. Understand this is very, very important for us to understand how NMR works. Richard Ernst of Switzerland was rewarded a Nobel Prize in 1991 for his contribution to the development of methodology of high-resolution NMR spectroscopy. Kirk Withrick, also of Switzerland, was rewarded a Nobel Prize in 2002 for his development of NMR spectroscopy for determining the three-dimensional structure of biological macromolecules in solution. Paul Lauterbur of the United States and Peter Mansfield of United Kingdom were rewarded a Nobel Prize in 2003 for their discoveries containing magnetic resonance imaging. How exactly nuclei are resonated? Let's move on to the next slide. In the last slide, we have talked about RF pulse. Why can an RF pulse resonate the precession of nuclear magnetic moments? First, we need to understand what an RF field is. In brief, An RF field is an electromagnetic field oscillating at radio frequency. Note that it does not oscillate mechanically, but in real time it does oscillate due to the alternating electric current in the coil. Because when a current flows through a coil, it produces a magnet in the magnetic material surrounded by the coil. And when the current is alternating, the magnet we got is oscillating. The application of an RF field in NMR is explained in the first statement. It says that in practice, nuclear magnetic resonance is achieved by exciting nuclei with an oscillating magnetic field that is perpendicular to B0. And mathematically, B oscillate can be decomposed into two rotating magnets, B1 and B2, such that with a vector equation, B oscillate is equal to B1 plus B2 and equal to 2B1 cosine bracket omega naught T EX, where B1 is equal to B1 times bracket cosine omega naught T EX plus sine omega naught T EX, which rotates anti-clockwise, and B2 is equal to B1 times bracket cosine omega naught T EX minus sine omega naught T EY, which rotate clockwise. This is depicted by the graph on the right, where cosine omega naught T and sine omega naught T are the X and Y components of B1, respectively. With the time increases from 0 to T, B1 then obviously rotate anti-clockwise from the X-axis to the position in the graph. So what? We have two rotating magnets now. By the right-hand rule, with the thumb pointing to the direction of B0, the magnetic moments mu j with positive gamma precess anti-clockwise in the direction of what the other four fingers point to, which is the same as the rotational direction of B1. Therefore, only B1 induces the nuclear magnetic moment to resonate, because it has the same rotational direction and frequency as the nuclei's precession, and appears to be static to every mu. A good example is the static objects we see in the Earth. None of them appears to be spinning, though the Earth spins all the time. Another example is a static object we see on a closed merry-go-round. When we are on it, we can see the object spinning only when we are outside the merry-go-round. With the fundamental equation of NMR, we knew that mu j's will then also precess about the axis of symmetry of a cone in the direction of B1, because it provides a torque that causes all those mu's to rotate about the direction of B1, thereby forcing every mu, and hence the M0, to swing or resonate away from its equilibrium orientation. This nuclear magnetic resonating process is also called nuclear spin excitation. Note that B naught that rotates at minus omega naught radian per second has no resonating effect to the nuclei at all in this case. It only will if the gamma is negative. Now we want to introduce two important concepts in NMR theory: the laboratory frame and the rotating frame. Let's begin with a recap about the NMR frequencies we have learned. One of them is solely with the applied magnetic field, and the second one is with an additional local magnetic field. We will denote them with lowercase omega and uppercase omega, respectively. Substituting the equation 1 into equation 2, we get equation 3, i.e., capital omega j is equal to bracket lowercase omega naught minus lowercase omega j in radian per second, where lowercase omega j is equal to sigma j times gamma b naught. And of course, it is equal to sigma j times lowercase omega naught radian per second. This means that lowercase omega j is simply a fraction of lowercase omega naught. Note that in our teaching, the unit for angular frequencies is often radian per second, not hertz, because we want to get rid of the factor pi in all relevant formulae. Apparently, if sigma j is positive, capital omega j is then less than lowercase omega naught, causing it to precess slower, and hence the nucleus is shielded from B naught. Otherwise, it is de-shielded. What are they in relation to a frame of reference? Here, the first statement says that in a static frame of reference called the laboratory frame, similar to an observer being outside a merry-go-round, nuclear dipoles precess at capital omega j radian per second about the direction of B naught, usually in megahertz. In a frame that rotates at lowercase omega naught radian per second, called the rotating frame, similar to an observer being on a merry-go-round, nuclear dipoles precess at lowercase omega j radian per second, usually less than a few thousand hertz. So, the lowercase ones are much, much slower. And they are stored and displayed in NMR time domain data and frequency domain spectra, respectively. In summary, we have learned three related precessing angular frequencies. The first one is lowercase omega naught, which is the frequency in the presence of B naught only. The second one is capital omega J, which is the frequency in the presence of B0 plus the local magnetic field due to the nucleus' immediate neighbors. And the third one is lowercase omega J, which is the frequency in the presence of local magnetic field only. You are expected to clearly remember the differences. In slide 20, we said that nuclear magnetic resonating process is also called nuclear spin excitation. Now we want you to view this in different frames of reference. On the left is a view of the excitation in a laboratory frame, where M0 was initially on the z-axis of a three-dimensional Eulerian frame at t equals 0, which is aligned with B0. When a 90-degree pulse B1 on the x-axis is applied, M0, being a summation of magnetic moments, then precesses under the effect of both B0 and B1. It will then precess about the B0 direction and the B1 direction simultaneously. This results in a spiral trajectory that brings M0 down towards the xy plane, while it is also spinning about B0. The spiral curve in the graph shows how the spike of M0 moves towards the xy plane. In the end of pulsing, M0 lies on minus y-axis. The dotted circle in the graph shows how B1 rotates, as shown in the equation below. How about the view in a rotating frame that rotates at omega naught radian per second? As shown on the right, M0 will then be seen to swing down to the minus y-axis about B1 only, where no rotation about B0 is seen. The dotted curve here shows how M0 swings toward the xy plane. Note that B1 here is static, and hence, in the equation below, there is no more oscillating component. And finally, be aware that on both figures, the right-hand rule applies to the rotation of M0.